In order to convert a decimal number into a binary number, I must first create my places. To begin this, I'm going to be starting in the very first column of my grid with the number 1. And then I'm going to move to the next cell to the left and place a number 2 in this value. And then I'm going to be placing the number 4 in the next cell next to the 2. And I'm going to work my way from right to left, doubling each previous number. So 4 times 2 is 8. And the reason why I'm doubling that is because I'm going from decimal into binary. Binary is a base 2 number system, hence the doubling effect as I go from right to left. So the next number is going to be 16, and the number after that is going to be 32, and the number after that is going to be 64, and the last number I'm going to be dealing with is 128. This is an 8-bit system. I began with 0 and worked my way up all the way up to 7, simply just doubling each number. Another way people have been doing this is looking at the base, in this case 2, and then looking at the place, like the very first column is 0, and taking the base and raising it to the place. 2 raised to 0 equals 1, hence the first value, the first column, if you will. And then 2 raised to 1 equals 2. And then 2 raised to 2 equals 4. As you start to see, my place values are starting to work themselves out. 2 raised to 3 equals 8. 2 raised to 4 equals 16. 2 raised to 5 equals 32. 2 raised to 6 equals 64. And last, 2 raised to 7 equals 128. That's a simple formula. I like to call it the base place formula. Take your base, in this case binary, and raise it to your place. Our places, as I'm going to illustrate, are going to be in green, are 0, 1, 2, 3, 4, 5, 6, 7. And so we take the base, 2, raise it to the index, or the place. So 2 raised to 0 equals 1. 2 raised to 1 equals 2. And that's the very first step before we convert a decimal number into binary, is we must lay out our grid. So we have 128, 64, 32, 16, 8, 4, 2, 1. Let me clear out the unneeded information now that I established this. Now, the red numbers are going to represent my place values. The black numbers I draw down are going to represent my decimal number. If I'm going to try to convert the number 146, now notice how I called that. I said 146. That's a decimal number. I could try to write a little 10 in here to let you guys know that this is a decimal number, but from now on, if you see a black number, I want you to think of that as being a decimal number. And my goal in this screencast is converting that decimal number into a binary number. So I'm going to write binary in blue, decimal in black, and then any place values I have to indicate, they'll be in red. So the next step, step 2 in the process of converting a decimal number into binary, begins with me asking one logical question. Which one of the red numbers comes up to the decimal number that I'm working with without going over it? So which of the red numbers comes really close to 146 without going over it? So 1, yeah, it's close, but it's not nearly as close as 2, and 2 is not nearly as close as 4, and 4 is not nearly as close as 8, and 16 is not nearly as close. And so we keep on working our way, and we say, oh, 128 is the closest number, the closest place that we have that comes to 146 without going over it. Since that's the closest one we have, I'm going to put a number 1 underneath the 128. After I do that, I'm going to take the 128 and remove it away from the 146. So I subtract 146. Subtract 128 from 146. How's that? Let's see. 146 minus Well, looks like I need to borrow, so this becomes a 3. And then I carry this over and I get a 16. 16 minus 8 is 8. 3 minus 2 is a 1. And then we have, whoops, and I apologize, I told you I was going to use black for decimal numbers, so let me do that. So we have an 8 here, and then we have a 1 there, and then a 0. So that's 18 in decimal. And then I got to repeat myself. I have to ask myself which one of the place values, which one of the red numbers, is going to come the closest to 18 without going over it. Well, looks like 16 is the candidate, so I'm going to draw a 1 underneath column 16. And then the question becomes, what do I do about 64 or 32? Well, since I haven't used them, I can fill them in with zeros. So I have a 1 in the 128, I have a 0 in the 64, and a 0 in the 32, and a 1 in the 16. Well, I repeat the steps. I remove 16 from my 18 decimal number. So I'm just subtracting 16 from 18. And what am I going to get? Well, that's just going to be a decimal number of 2. And then I ask myself the same thing. Which one of the red numbers, the places, comes close to without going over that decimal number of 2? Well, 2 is the best candidate. 2 goes the closest. In fact, 2 is that number. And so now I subtract 2, the red 2, from my decimal 2, the black 2, and I get 0. When I get 0, after I do this work, I stop and I fill in all my missing values with zeros. So I put a 0 underneath 8, a 0 underneath 4, and a 0 underneath 1. So the binary equivalent to 146 would be a 1, 0, 0, 1, 0, 0, 1, 0. And that's it. That's how we convert a decimal number into binary. Let's look at another example. What if I want to take decimal number of 119 and convert it into a binary number? Well, remember the simple steps. Create your grid. In this case, I have 128, 64, 32, 16, 8, 4, 2, 1. Now, the grid could be wider. I could go up to the 256 or 512 or 1024, but I'm just trying to keep it simplistic. The formula is very universal. Just scale it as you need it. And I ask myself, which one of the red numbers comes close to the 119 without going over it? So I look at this and I say, well, 64 is the closest. 128 would actually go over 119, so that would violate my rule, and therefore I would have to put a 0 underneath 128, but I can put a 1 underneath 64. After I find the best match, or the closest match, I will subtract that value from my 119. So I remove 64 from 119, and I get a new decimal number. So 9 minus 4 is 5, and 11 minus 6 is also 5. So I'm left with 55. And I ask myself again, which one of the red numbers comes closest to 55 without going over it? Well, the best candidate in this case is 32. So I put a 1 underneath the 32, and then I repeat my step. Subtract the 32 from the 55, and I'm left with, let's see, 23, is that correct? Seems right. Please, folks, check my math. Sometimes I do make mistakes, and as it will, it'll affect the binary. And I repeat, and I ask myself, which one of the red numbers, which one of my places, comes close to the 23 without going over it? Looks like 16 is the best candidate. Now I subtract 16 from 23. And I'm left with, let's see, we got to borrow from that. And I have 13 minus 6. Looks to be a 7. Get it in there. And then I ask myself which one of the places comes close to 7 without going over it. So the closest red number I have is a 4, so I place a 1 underneath that. Since I skipped over the 8, I'm going to put a 0. Now I'm going to subtract the 4 from the 7, and I'm left with a 3. And then I ask myself, which one of the red numbers comes close to 3 without going over it? The answer to that is going to be 2, so I put a 1 underneath the 2. And I repeat, I remove the 2 from the 3, so I subtract 2 from 3, and I'm left with a 1. And obviously, which number comes closest to 1 without going over it is going to be my last place of 1. So 119 in binary is a 0, 1, 1, 1, 0, 1, 1, 1. Now, when I read my binary number back to you, I'm always starting with the leftmost digit and reading towards the right. So I start off with the very first place of being 0, then a 1 underneath the 64, a 1 underneath the 32, a 1 underneath the 16, a 0 underneath the 8, a 1 underneath the 4, a 1 underneath the 2, and a 1 under the 1. Alright, so that was us taking a decimal number of 119 and convert it into binary. Let's try a marathon decimal number of 255 and see if we can convert that into binary. So I'm going to come over here in my scratch area and write 255. And then I got to ask myself, which number comes close to 255 without going over it? Well, the closest one is 128. And now I'm going to subtract 128 from my 255. And I'm going to get, let's see, looks like I can do some borrowing from here. So I get a 4. So I have 15 minus 8. And let me change my color. There we go. 15 minus 8 is a 7. 4 minus 2 is a 2. And 2 minus 1 is a 1. So I have 127. And I have to ask myself which one of the red numbers, which one of my places comes close to 127 without going over it. And that's 64. And I need to subtract the 60, I need to remove the 64 from the 127. So just take 127 minus 64. So I'm doing this in my scratch area over on the right. And let's see, let me convert my colors back. So 7 minus 4 is 3, and 12 minus 6 is 6. And then I repeat myself. Which one of the places, our red numbers, comes close to the 63 without going over it? And that's going to be a 32. And I subtract the 32 from the 63. And I should be left with 31. So now that I have a 31 decimal number, I have to repeat the process and ask myself which one of my red numbers, my places, comes close to 31 without going over it. And the answer is going to be 16. So I'm going to draw a 1 underneath 16. And then I'm going to remove 16 from the 31. So I'm subtracting 16 from 31 over here in my little scratch area. And what I'm going to end up with should be a 15 in decimal. And then I repeat myself, which one of my places comes close to the 15 without going over it. 8 is the closest, so I put a 1 underneath that. And then I subtract the 8 from the 15. And what I'm left with is 7. And then I can say that 4 is the closest number that comes up to 7 without going over it. So I put a 1 underneath the 4. And then I remove the 4 from the 7 by just taking 7 minus 4. And that leaves me with a decimal number of 3. And I can see that 3 is comprised of 2 parts, 2 plus 1. So in the interest of saving time, and because I'm running out of my little scratch area, I'm just going to put a 1 underneath the 2. And then I would get 3 minus 2, which equals 1. And then I put another 1 underneath that. And this is where you've heard me refer to when it comes to the subnet mask, that when you're stuck with a 255 in an octet, you're going to get all ones. And as we can see, 8 ones in binary 8 ones binary is the equivalent of 255 in decimal. Now, a lot of students tell me, well, Nick, if you have 8 bits, 2 raised to 8 is 256, not 128. And they're absolutely right. But I go from 0 to 7. That's like saying I go from 0 to 255. That gives me a total of 256 possibilities. So let me draw that here. Let me just use this area right here to illustrate what I'm trying to talk about. If all ones are 255, then all zeros would simply be 0. That gives me a combination of 256 unique possibilities, with the first one being all zeros and the last one being all ones, or translation 255. So when I take 2 raised to 7, I'm given a 128. So a 1 in the 128 is simply there, then all zeros. The next combination of zeros and ones, in other words, the next number, 129, would be a 1 followed by all zeros, then another 1. And then the next combination after that, 130, is a 1 followed by a bunch of zeros, then a 1 in the 2's place, then a 0. And obviously the next number after that would be 131, which would be a 1 here, then some zeros, then another 1, then a 1 again. Now in another screencast, I show you how to count in binary. That just helps us understand the structure of binary. But for this course, all we really need to do is learn how to convert from decimal to binary and binary back to decimal. Let's convert one more number from decimal to binary. Let's start with the number 200. And this will be our last example, so I'll just go through the steps that I naturally would do when I'm converting a decimal number into binary. And so I say 128 is the closest number that comes up to 200 without going over it. And we subtract 128 from the 200. And I'm going to be left with, let's see, we got to do our borrowings. And that gets me a 72. And what do I see? 64 being the closest number, going up to 72 without going over it. Subtract 64 from my 72, and I'm left with 18. Is that right? Let's see. Oops, sorry, not 18, 8. And I put a 1 underneath the 8, and I fill in all my missing places with a 0. So 200 in binary is the same as saying 1 1 0 0 1 0 0 0. In this screencast, we just basically discussed how to take a decimal number and convert it into binary. In another screencast, I'll show you how to do the exact opposite, how to take a binary number and convert it back into a decimal number. Throughout this semester and other courses, you will find this to be very useful. In this course, the networking course, we will use this technique to determine what a network address is and see how we actually have our devices use bits to communicate with each other and determine pathways to send the messages out. Thank you for your time, and I'll see you in the next screencast.